Welcome to lecture 17 on risk management and insurance. In this lecture, we work through an example for the whole or universal insurance contract that we discussed in the last lecture. Now let's consider a benefit fund with 1,000 members. So the insurance company has 1,000 members. The time horizon is 1 year, so we just look at the 1 year of operation of the insurance company. The death benefit that the member gets is $2,000. So when a person dies, okay, $2,000 will be paid. Now, the annual mortality rate, we assume it is 1%. Then we apply a safety loading of 10% above the fair insurance premium. And we assume that the probability of ruin is 1%. So the insurance company would like to achieve a probability of ruin of 1%. This may be actually just set by the managers of the insurance company, or actually it could be set by the government or some regulatory agency that supervises the insurance company. So the question is, how much initial equity capital does the insurance company require to achieve this maximum probability of ruin of 1%? Let's first focus on this mortality rate. Now here you have the mortality of people in South Africa according to age. It's actually death per 1,000 people. So 10 people deaths, that would be a rate of 1%. That 10 out of 1,000. So you have your 2%, 4%, 6%, and so on. Now, you see here when you are very young, as a child, okay, the death rates are very, very low. So here it's 5 to 9 years old, 10 to 14 years old. So if you survive the initial few years, okay, then during your childhood, a very low death rate. And then it starts to rise slowly, and then here around 70, then around 70 years old, okay, then it really starts to rise very fast. So here, a 70-year-old, okay, the death rate is 70 to 74 year, the death rate is 4%. Now 1% is here in the late 30s. So people between 30, the cohort between 35 and 39, okay, has a death rate of about 1%. Now I have here different lines, but they just give the death rate in different years. But naturally, those lines are very close together. So our example would apply to a cohort of people from 35 to 39 years old. They have a death rate of about 1%. So the expected number of dead people, remember the fund has 1,000 members. The death rate is 1%. So the expected number of death is 10. And then the premium income with loading, lambda, okay, just go to equation 1. Remember, it's a fair premium income. Actually, we call that pi. Here, I'll just write it out. The fair premium income, it's the expected number of deaths times the payout. So it's 10 times 2,000. The payout will be 2,000, okay, when the person dies. We expect 10 people will die. So the fair premium is 20,000. And then the insurance company applies this loading of 10%, okay, to the safety loading of 10%. Okay, so in the end, okay, the insurance premium will now be 22,000. So it's more than the fair premium because of the safety loading. The safety loading protects the insurance company against being broke, against ruin. Now let's suppose the death occur with a known average rate per year, as that's the expected value, in our case 10 dead people per year, and independently of the time since the last death. So death, the dying of people is actually independent across time. In that case, you can use the Poisson distribution. Now, the Poisson distribution is fully described by its expected value, which is the number of dead people, so number 10. So the Poisson distribution has actually only a single parameter. It's a one parameter distribution. So this notation here stands, okay, for the probability that there are k number of deaths if the expected value of death, is let's say 10. So probability that you have k number of deaths. That's a random variable x takes the value k. So that's the density function, and here you have the expression for it, and you see, naturally k is just given. We have only a single parameter, which is the mu. That's the expected value, and at the same time, it's also the variance of the random variable x. The Poisson distribution, you always use the Poisson distribution if things happen infrequently. So we say the Poisson distribution you apply to rare events. If those events happen with a known average rate and independently across time, then you can use the Poisson distribution. For example, you can use a Poisson distribution to model accidents of airplanes, airplane accidents. That happens that happens at a known average rate and independently across time. If there is an accident, this does have no link to the next accident, of an airplane. So if you have rare events, then you can use the Poisson distribution. Originally, the Poisson distribution actually was developed. Poisson, he lived in Germany, and he actually developed it for horse kicks in the Prussian army. The Prussian army, there were actually about 10-12 soldiers died each year because they were kicked by a horse. And this followed a Poisson distribution. It actually happened at a known average rate of about 10-12 dead soldiers per year. And if one soldier got kicked, this was independent of the next soldier of being kicked. Now, I learned this example about the horse kicks in the Prussian army, when I studied statistics in Zurich. And I thought, now my statistics book is a bit old. Horse kicks in the Prussian army in the 19th century. But actually, I just saw, recently I saw a modern book in physics, and they still use actually the example of Poisson of horse kicks in the Prussian army. But actually, there are naturally other rare events, where you can use like accidents of airplanes and so on. So here, you have the Poisson, the probability, of having up to 18 dead people if the expected value is 10. That probability is 99.3%. And you get this very easily out of Excel. Just give those commands into Excel, and naturally also in R, there are commands. You can use also the the table, okay, in the book by Zweifel and Eisen, okay, which is mentioned at the beginning of this chapter. But naturally today, okay, you probably will use either R or you will use, okay, Excel. So the probability, the Poisson-Landerwave with an expected value of 10 assumes values of up to 18 with probability of 99.3%. The probability is that you will have up to 18 dead people if the expected value is 10, okay, will be 99.3%. So with an expected value of 10 people, the probability that there are up to 18 dead is 99%. Okay, so the probability that there are more than 18 dead is just 0.7%. So actually we have to cover 18 dead people, okay, with the funds. The insurance company should have enough funds to cover 18 people, and such a probability that it will be ruined will be only 0.7%, less than 1%. Okay, it will be in trouble if there are 19 dead people, 20 dead people, and so on, but that probability is very low if the expected value is only 10%. So if the insurance company can cover up to 18 people, then it will stay solvent at the 99.3%. If it has enough funds to cover 18 people, then it will stay solvent at the 99% probability. And the probability of ruin, okay, will be only 0.7%. It will be ruined if it's 19 deaths, 20 deaths, okay, more people, then actually probably the insurance company is in trouble. So let's plug in everything in equation 9. So we have here, just before we calculated the risk premium, it was 22,000. We calculated the insurance premium. Sorry, it's insurance premium. The premium income. We calculate the premium income. It's 22,000. So the premium income 22,000. And then actually we have the insurance payout, the death benefit 2,000. And we want to be able to cover 18 people. So actually what we need here, actually initial capital of 14,000. Okay, our expenses will be 36,000. But then we have the premium income of 22,000. So we need capital of 14,000. So an initial capital of 14,000 will guarantee us solvency with a probability of 99.3%. So the probability that the company will be ruined, okay, is less than 1%. And that's what we were looking for. You see, the probability of ruin should be 1%. Now we will have here a bit less than 1%. We will get 0.7%. But that's naturally even better. So the available funds for the year, we look at a single year, are the 40,000 initial capital plus the 22,000 of premium income. It's a 36,000, that's our available capital. And so probability that we need more, okay, is just 0.7%. So with 36,000, okay, we will stay solvent with a probability of 99.3%. Okay, so here I again drew the loss function for that year. Now, let's assume that the initial capital is not 14,000, but it's less. It's only 10,000. And the insurance company is unable to raise more capital. Okay, in that case, it could actually increase the safety loading and charge a higher insurance premium to stay solvent with the required probability. So if you look at it this way, now actually the initial capital is given and you want to solve for the safety loading. Before, we did it the other way around. The safety loading was given, and we solved for the initial capital. But now let's turn it around. Okay, you just take equation 5 and 9 and then solve for lambda. So you have here, okay, the X, that's insurance payout when a person dies. We have the expected number of dead people, so that's a 10. Okay, we want to be able to cover up to 18 dead people, because that guarantees us a probability of solvency of 99.3%. And then actually the initial capital is now set at 10,000, and the insurance company cannot rise more. So lambda turns out to be now 30%. So the safety loading will increase now from 10% to 30% in order to stay solvent at 99% probability. Okay, the insurance company may try that, but okay, naturally then okay, the demand for insurance will decline. So maybe you cannot do that. That already finishes today's lectures. So thank you.